In this video, we'll write the electron configuration for iron, Fe, and the Fe2+ and Fe3+ ions. So to do that, we'll start out with iron on the periodic table. On the periodic table, iron has an atomic number of 26. That means it has 26 protons. In Fe, iron, on the periodic table, it's neutral. It doesn't have a plus charge after it. So the number of protons are going to equal the number of electrons. So you have 26 electrons to write the electron configuration for iron. We'll use this periodic table here broken up into these orbital blocks to help us write the configuration. You can also use this chart here. There's a link in the description on how to do that. I think this is a better way to do it though. So let's get started. Iron, 1s2. That's where we start. We have 1s1, 1s2 because s orbitals can hold up to 2. Then we go to 2s. We have 2s1, 2s2. We've used 4 electrons. We have 26. Then we go to the p's. P orbitals can hold up to 6. So we'll go 2p, we'll put 6 in there, 3s2, 3p6, and we come back around to 4s2, and this all adds up to 20 electrons. So we have 20 electrons right now, we need 26. We get to the 3d. D's can hold up to 10 electrons, but we don't need 10, we only need 6. We have 20 here, so if we put 6, that'll give us 26, and this is the electron configuration for Fe, iron. Often you'll see the 4s after the 3d. As we get further into the periodic table, that makes sense because this 4s, these electrons are going to be lost to form ions first, so we put them last. Either way, these are the correct orbitals, it's just the order we're talking about. Let's write the condensed notation for iron, and then we'll use that, we'll remove some electrons to form the ions here. So in our configuration, we have 3d6, 4s2. So we go 4s1, 4s2, and then 1, 2, 3, 4, 5, 6. That's where iron's at on the periodic table. To write the condensed notation, we go back to the noble gas that's before iron, and that is argon. So we have our argon here, and we're going to write Ar, and then we're going to put brackets around it. So we have everything here up to Ar, then after the Ar, we have 4s2, and then 3d6. We said we were going to put the 4s2 after the 3d6, do that, and then we'll use this to write the electron configurations for Fe2+ and Fe3+. So here's our full notation for iron, and then this is the condensed notation just for Fe, iron. So we'll take this notation here, and because it's a 2+, that means it's lost 2 electrons. Electrons are negative. When you lose electrons, you become more positive. So iron loses 2 electrons, and we'll get rid of this 4s2 here, and that's the electron configuration for Fe2+. For Fe3+, we need to get rid of 3 electrons. So we'll get rid of these 2 right here. We'll change the 6 to a 5, and this is the electron configuration for Fe3+. So there you have it, the electron configuration for iron, and then the electron configuration for Fe2+ and Fe3+. This is Dr. B, and thanks for watching.
The thermite reaction, which is the reaction of aluminium and iron oxide, is used to make iron, and because aluminium has much stronger bonds to oxygen than iron, that the reaction produces an enormous amount of heat. And you can use this for welding pieces of metals together.
So this is a thermite mixture. It's a mixture of iron oxides and aluminium powder. And we're going to do some redox chemistry, and we're going to generate some molten iron, which will hopefully stream from the bottom of the flower pot. So here you can see the black particles of the iron oxide and the silver particles of the aluminium powder. So we get some heat on this, we start an instantaneous redox reaction. So the aluminium and the iron oxide swap oxygens. So the aluminium will become oxidized, the iron will become reduced. Hopefully we'll generate a lot of molten iron, which should come from the bottom of the test tube of the flower pot.
All right.
Right.
Now, there's a story about students in Berkeley that some students decided, or a group of students decided to do a practical joke on a tram, which of the sort that has one door when you go in and another one where you go out. So a big group of students queued onto the tram and got into the front, and there were enough of them so that they could actually come out at the end, at the other door, and form a loop. So they were just going round and round and round. So the tram couldn't leave because there were just more and more people getting on.
Could have run out of tape.
And while they were doing this, other students went down under the tram and set off 2 thermite reactions and welded the wheels, metal wheels of the tram to the steel rails, so that when the tram tried to leave, when the students eventually stopped going round and round, it was firmly welded to the tracks and couldn't move at all.
It's gone out.
Talk me through what's going on, mate.
So instantly the thermite reaction starts, and you can see that it's so hot it's burnt a hole through the bottom of that terracotta flower pot. But if we go in close now, Brady, you can see all that really quite nice molten iron. Now that's so hot that the iron itself has melted and it's formed this really quite big goo in the bottom on the sand.
Do you encourage these sort of practical jokes?
No. Our students are far more responsible.
So as soon as the firework or the sparkler hit the top of the thermite reaction in the top of here, it started off the instantaneous redox reaction. So this was where the metals were fighting for the oxygen. The aluminium won that battle, and the aluminium came out of this reaction as aluminium oxide. The iron was reduced, and we can see that now in the bottom, which is really hot. So I'm not going to get too close, but you can see all of this really, really hot iron. So the iron was molten, it dribbled out through the bottom of the flower pot, and it's now cooling.
Well, it didn't dribble out the bottom of the flower pot.
Well, it smashed its way out of the flower pot.
Well, you can say that iron is in my blood. It's in your blood as well. It's iron that gives hemoglobin, the red pigment in your blood, its red colour.
So the reaction we saw was about 5 minutes ago, and the iron that was generated is still glowing red hot, and you can see it's fused itself to the bottom half of the flower pot, which it broke in its tumultuous step forward.
It is an absolutely central molecule to element to life, except for crabs, which use copper, but you'll have to hear about that later.
So iron's a really, really abundant metal, which is used as lots and lots of structural materials. So you can see lots of pieces of iron around some of the racking, and even in fact some of these pieces of equipment have got high iron contents. They've got other elements mixed with them to form alloys like stainless steel.
I have an extremely long-standing interest in its chemistry, and in particular I made one compound of iron, so-called iron tetracarbonyl, which had 4 groups round it, and everybody had expected that it would have a shape like one of these, shaped with tetrahedron like that, whereas in fact it turned out that it had a much more irregular shape. The 4 groups were arranged like this. And so ever since this, every time I hear the word iron, I get quite excited.
So this is iron wire, okay, and you can see this is a very small wire. It's 0.2 of a millimeter in diameter, and you can see that the shiny material underneath is iron that hasn't undergone oxidation. So this is where it's been protected from the oxygen in the air. Now if we look at the iron at the top, we can see this looks really familiar, especially because it looks like the rust that we might find on the bottom side of some of our cars. So here's some iron oxide on top of the iron.
The very first chemical experiment I did chemical reaction was with iron, and I think the same is true for many generations of school children. I heated up iron and sulfur together and made iron sulfide, sort of blackish solid, but then we put acid on it and got a terrible smell of bad eggs, and this was my introduction.
Bye.